Hi, my name is Noah Gift, and I lecture at some of the top universities in the world. And in this lecture, what I'm going to talk about is optimization problems. So in particular, we're going to get into greedy algorithms, and we're going to talk through a famous problem called the traveling salesman problem. And the reason why it's studied so much is there isn't a perfect solution for the traveling salesman problem. Instead, there's a good solution for the traveling salesman problem. There's actually lots of good solutions. And so the idea would be something like this. Let's say you wanted to visit California and you wanted to visit as many cities as you could, but you didn't want to spend extra time traveling, and you also want to minimize the amount of gas that you are actually buying. It's very expensive actually to buy gas in California. So let's say you wanted to, again, maximize, let's say 100 cities that you wanted to visit, and what would be the correct path? Would you want to go from, let's say, San Francisco to San Rafael to Mill Valley to maybe Fairfax all the way down to Point Reyes, and then from there go to Point Reyes, go to Santa Rosa, just as an example? Or would you want to pick a different route where maybe first you go to Santa Rosa, California, which is 50 miles away from San Francisco, then go from Santa Rosa down to Point Reyes, and from Point Reyes go to Fairfax, and then from Fairfax go down to let's say Palo Alto? You can see it's limitless. Really, there's without bounds. You can go and visit all of these different cities. And so you need to come up with a better solution. And so the greedy algorithms are the way to solve that problem. So that's what we're going to cover in this lecture. It'll take about an hour to cover optimization and greedy algorithms, and looking forward to you mastering this material, and see you soon. Perfect. So I want to talk about optimization, and it's a fun topic because it really involves the real world optimization, and you see this all the time when you're dealing with many different kinds of problems. And I think a good one to talk about initially is this problem called the TSP, or the traveling salesman problem, and it's been around for a long time, I think for centuries. And the core of the problem is basically that you have a lot of different locations that you need to visit. It could be, let's even take the Silicon Valley, right? The Bay Area. You could say that you want to visit, San Francisco. You want to visit Palo Alto. Maybe you want to visit San Jose. You want to visit, so here we go, San Jose here, and then you want to visit maybe also Santa Cruz. There's tons of different places, and you also have, let's say, Santa Rosa. You have all these different locations. Maybe you have 100 locations, right? And from here, from San Francisco to Santa Rosa, I know that it's 50 miles. From San Francisco to Palo Alto, that's 50 miles. But this is north. It's 50 miles north. Palo Alto, it's 50 miles to the south. And then San Jose is probably, let's say, like 40 miles to the south. Santa Cruz is probably maybe 80 miles to the south. But you get the idea, is that you're starting in some location. Maybe you're starting there, but you need to go to all these different distances, and some of them are farther than other distances, and you need to visit all of them, let's say, in one day. And what is the right direction and route to take so that you can go the shortest distance? So the goal you're trying to solve is the shortest path. And there's been a lot of research on this problem, and part of the issue is that it doesn't have a perfect solution. And so this would be into the category of non-linear optimization. And the reason why it's non-linear is that really it's non-deterministic as well. So there isn't some perfect solution that you can solve for, and then you always get the shortest distance. If you're talking about hundreds and hundreds and hundreds of cities, and you're trying to figure out the shortest path to those, you have to figure out a different approach to solving the problem. Now, if you're talking about linear optimization, it's much easier, because in the case of linear optimization, you really just need to figure out the correct line here between what it is you're building, and you have a perfect solution. And that's what they use linear solvers for. And so there's libraries that do this in Python, for example. And these libraries in Python, one of them is Pyomo. Another one is, I think it's called CV is another one in Python. But basically the idea is that you can exactly pick the solution because the problem fits into a linear realm. With this shortest path type problem, where you're trying to figure out the shortest path, you have to come up with a different approach. And so one approach here that I'll spell out is that you can use a greedy algorithm. And what a greedy algorithm does is, the greedy algorithm says that basically every time I'm presented with a choice, I always choose the best choice. And so if you start off with one city and you have, let's say, 3 different choices, right? You have a choice here where you could go 5 miles, you could go 10 miles, or you could go 7 miles. In the greedy algorithm, you would always choose this choice. And then if you go then to another place and you have another choice again, and it's 7, 6, and 5, well, then you would pick the shortest path again. And there's been lots of research on this, and one of the reasons why it's helpful is that because of the fact that you don't know the correct solution, that the best solution that you can come up with at the time works out reasonably well. And you can even make things a little bit better by doing a random start. And what a random start does is that it allows you to basically try a bunch of different approaches and randomly pick, maybe there's 3 different cities that you could start at. You could start at city A, you could start at city B, and you could start at city C. Well, you could randomly go through here and choose one of the cities. And then what's nice about optimization is you can run a simulation. And with a simulation, you can choose how long you want the simulation to run. So if you're dealing with, let's say, 10,000 cities and you wanted to figure out the shortest path, you can randomly start. The algorithm would be basically random start, so we'll call this RS, greedy choice, so GC, and then you minimize. So basically, after you've done maybe many different iterations of the algorithm, you could go through and once you get to something that's a pretty good solution, let's say that one solution that you initially started with was 1,000 miles, and then you go through and you start running the simulation and you keep running a bunch of random simulations, then eventually maybe you get to a route that shows 500 miles. And so you say, you know what, that's good enough. 500 miles is not that bad. We'll go ahead and pick that. Now, you could have kept running the simulation, and maybe you can run the simulation many different times. And if you run it more, maybe you could get down to 480 miles as your smallest measurement. But it's really a time then becomes the limiting factor when you're doing these kind of simulations where it just depends on how much time you have, and then that will help you figure out what approach to use. So similar things happen with deep learning in particular. And so if we go to deep learning, which many people have heard of, and we look at, for example, the way they solve problems, is that it's a similar approach because of the fact that there isn't a perfect or optimal solution. There's a good solution though, and so if we look at an example of the way things get solved, let's say that this is where you want to get to is somewhere down here, which would be the optimal solution. and you have a function that's going to solve for the optimal solution. One of the things that deep learning does is it incrementally will get better and better results. So it learns the way to get the right answer. And so one of the ways that it does that is through something called the learning rate. Here we go. If I go through and I go down like this, and each time, and we'll call this the learning rate, LR, and the learning rate, I get a little bit closer to the answer. I get a little bit closer to the answer, just like in the other problem. I get a little closer to the answer. Eventually, if I have enough time and I have enough processing power, and basically I'll get to a good solution, right? So the optimal solution here. But this is where things like hyperparameter tuning, which you may have heard of before, comes into play. If we go hyperparameter here, that what happens with hyperparameter tuning is that this learning rate is something that you can tune. And so maybe some people don't want to wait for the default learning rate. And so what they do is they say, look, I'm going to change the learning rate to be really large. And I'm going to change it. Maybe it was at 0.03. We'll call this one 0.03 right here. The learning rate is at 0.03. I'm going to change it to like 15 because I'm in a hurry. Well, one of the things that can happen is that you'll oscillate back and forth. You'll just go back and forth and you'll get nowhere if you change the learning rate too high, because you're learning too much and you'll basically be thrashing. That's the way to kind of put this. So it's also something to be aware of with things like deep learning, is that there's a tuning that you have to do where you learn just enough information, but not too much, so that you can gradually come to the right answer. And this goes into maybe the core nature of how deep learning works. So let's just briefly talk about that real quick here. Again, so if we look at, let's say, machine learning on any cloud platform, but in this case, we'll talk about AWS, that we know that AI and machine learning, deep learning, it's all part of this category of AI, and inside of AI is machine learning. But machine learning and deep learning are just, deep learning is a subcategory of machine learning. So there isn't necessarily anything tricky that deep learning is doing that machine learning isn't really the parent category of. And machine learning has several different types. They have supervised, which means that you historically know the right answer and you're doing a prediction based on it. So it would be image classification, could be a good example. Unsupervised is you're trying to discover hidden patterns, but you don't know what the correct answer is. And then reinforcement would be regression and classification. So again, predicting the right answer based on historical data. And clustering is, I don't know what the right answer is, but I'd like to find some interesting patterns. And so what can machine learning do? Well, it can do predictions. It can optimize utility functions like what we were just going over, which is find an optimal solution. It can find hidden data, classify things. And so you can see all the different use cases for fraud detection, hidden patterns, training models, flagging transactions, recommendation engines. You can also target marketing, categorize things, customer service. In general, the way things work in a machine learning modeling pipeline is that you upload the data, you clean it up a little bit, and we'll go through some examples of that in a little bit. You create and train the machine learning model. You then evaluate whether it came up with a good result, and then you come up with a prediction. So really, machine learning is a combination of methods and systems. So it's predicting to predict new data from observed. It's extracting hidden data. It's summarizing data into executive brief. It's also optimizing and adapting. And again, machine learning has got these categories. You can see unsupervised, supervised, classification, regression, and then reinforcement. And so one thing to be aware of as well with classification, like categories like red or blue or regression, housing prices, is that this is all coming from knowing what the correct answer is. But reinforcement learning is about learning from the behavior of the environment. So it's like a robot vacuum. So a couple things that I will scroll down here to look at as well is that when you're doing machine learning, you're often looking at the features, and then those features go to solving the problem. But you also can do machine learning by using these high-level automated tools, which we'll get into in a little bit. And with these high-level automated tools here, you can just click a bucket, select the data set, create a data source. It'll figure out what the schema is. You select a target, and then you train a model. And you could do the same thing yourself by writing code. But one of the nice things about this particular solution is that it will go through here, train the model, and then come up with a solution with you just really selecting the right metric. And you can see typically what people use is something called area under the curve. And it's basically a sweet spot between, what's the right balance of false positives, false negatives, so that I can predict something correctly, classify it correctly. And you can also do the same thing with a confusion matrix. Those are other examples of this as well, and explore the performance. But in terms of the deep learning, which gets us back to what I was originally talking about with optimization, is that really the theory behind it is that in 1950 there was this a lot of academic activity all the way to the late 1990s, and in the United States, in fact, they would use neural networks to figure out which pilots in the Air Force would be good Air Force pilots, and because it was very expensive to train Air Force pilots. And so that was one of the famous use cases for it. And then from 98 to 2007, there was something called the AI winter, where most of the research had kind of stopped. People felt like there was really not a lot to be done with it. But then because of the GPU era, where we have these high performance GPUs, there's been a resurgence of thinking about deep learning. And deep learning is a multi-layered feed-forward neural network. And so the perfect storm for doing deep learning is cloud computing, the end of Moore's law. So basically CPUs aren't getting faster, and also cloud computing. So elastic storage and compute. There's all these datas now where people are voluntarily spending all their time clicking buttons, getting engaged with content and social media. And in particular, this has led to more and more neural networks in production. So let's talk through what a neural network is and how it applies to that last diagram. So a neural network has neurons here. These are the neurons. There are hidden layers that are used to basically train the model. And as the data goes through, what happens is that it's collectively trained in layers to learn complex functions. So it's incrementally learning the correct solution, and then eventually it goes through and it comes up with a prediction. So this could be, for example, maybe classification prediction, where these are 4 different categories. And then with a recurrent neural network, which is used a lot in time series data or speech, you'll see that, in fact, they will be not go basically from left to right here, but they'll feed back into each other to handle sequential data. And again, with this whole pattern here, what's happening is that you're doing what we talked about earlier, which is you're crawling down this solution until you get to the optimal solution. That's really what is happening when you're coming down here. There's lots of different deep learning use cases. Text analysis is a big one, right? So looking for sentiment, Also looking for brand affinity, time series data, financial log analysis, recommendation engine. And you can do a lot of this stuff with both writing the code yourself, or you can also do this with doing AutoML. And in particular, what I was going to cover next here is talking a little bit about the intuition behind neural networks. And so a great way to learn the intuition behind neural networks here is to look at this TensorFlow Playground. And what this TensorFlow Playground does is it lets you capture the complexity of a neural network all in a web page. And so you can learn about how a neural network works. Because again, it looks, if you go back to this, you can see it. You have an input, you add these layers, and then you go through and you classify something. So with this neural network playground, you don't have to write any code at all. You have everything at your fingertips here. And the goal would be, here's your features right here. You have 2 features, and you want to classify things. You basically want to classify between these 2 different colors. And so you can see this is not a very complex data set. And it's got a pretty clean division here. So let's go ahead and just leave everything default. And if I click on this button, you can say every single time it learns a little bit more. So it's kind of going down, solving the correct solution, that the training loss goes to hopefully 1 or to 0. And then the test loss will also be 0. So there we go. See, the training loss went to 0. And now the test loss is still 1. And there we go. So now it stopped. So it took 862 iterations to slowly learn the information piece by piece, because each of those neurons is learning a little bit more and then passing the what it's learned down to the next layer. And it really does work where you're hopping down slowly. You're slowly hopping down to eventually get to where maybe the loss is 0 here. Now, let's say again that we want to get to the solution quicker, because maybe it's a really big problem. Like this is just a toy data set, but maybe it's a huge data set and we can't wait for 1 month to train the data. So maybe the deep learning engineer says, okay, I know what the solution is. I know that the learning rate is how quickly I learn. Well, why don't we just make it go to 10, right? What could go wrong? So let's try that. Let's refresh everything here and let's change the learning rate to 10. And hopefully it's way quicker now. But what happens? So what happens is that in fact, it just does nothing. It just oscillates back and forth because it's learning too much information at the same time. And it's basically hopping back and forth across to nowhere. And it's not learning anything. It's just sitting here going back and forth, back and forth, back and forth, thrashing. And so this kind of highlights the fact that there really is, there's no free lunch, right? You have to tune things incrementally. So before we know that the 0.003 was, I think it was actually 0.03 if we refresh everything. Yeah, 0.03 was the default here, but maybe we change it to 0.1. Let's try that. Let's see if we can change it quicker. And now we see that in fact we can go a little bit quicker to, there's less epochs, and I believe that it will go to 0 soon. And let's see here, let's wait for it. Maybe it doesn't go to 0 soon. So we can see that in fact it got the training loss, which is basically the data that we're training on. It got there much quicker, but it still is slightly overfitting. That's what that means, is that when we test it on new data, it's a little bit, it's too in tune to the training set. And so what we can do to fix this problem is that we can add some regularization here. And what regularization does is it penalizes the ability to learn. So it can prevent overfitting. And so if I click on it now, we can see that it will go very quickly it will learn the information, and now hopefully this test loss is actually quite small, right? It's less of a loss than it was before, and it seems like it's maybe improving. And then we can even change the regularization rate, so we can add a little bit extra here. Try it again and see if that changes things. So the general idea with deep learning or any kind of an optimization problem is that there isn't necessarily a perfect solution, and it's a process of running through a bunch of simulations essentially and learning more and more information until you get to the correct solution. And that's kind of the core intuition behind deep learning. And if you want to try other deep learning problems here, like there's, it gets incrementally more difficult. Like if you go for this, for example, and you try to train this, it'll take a long time because of how complex this these 2 bits of data are. And you can see it'll take a long time to learn, and maybe I have to change different activation functions and maybe even add more neurons or add more hidden layers. And these are all things that are, things that you can kind of play around with to experiment with. But let's take a break from a second from this and then get into some actual code that I think will help explain this a little bit. So in particular, there's a piece of code here that has the routes. And so these are all cities that you would go through that would be the distance, right? So this would be Apple to Cisco would be 14 miles. By the way, this is real data. This is the Apple headquarters to CVX, Apple headquarters to eBay. These are all the different cities in the Bay Area that I will be traveling to. And so if I wanted to go through here and train my data on these routes, I would need to come up with a greedy algorithm. So here we go. Here's the actual algorithm. Here is a traveling salesman with random start, and a greedy path is that I would start with importing the systems module, and then import something called random choice. So this is an important thing to be aware of that we can take a look at with in Python. In fact, I have one other thing that I'll show in this repo, which is another notebook here that I think can be helpful here. And basically, notice that when you do a random, let's just go ahead and open this in Colab. Why it can be helpful to figure out an algorithm is that, let's say I want to randomly select one of these correct food choices for my meal, right? I don't want to pick. I either want an apple, banana, strawberry, but I don't care which one. I could just put those into a list, and then I could say from random import choices, and then say choices is equal to food, and then it would pick one of those choices. And if I run this, you can see that's an apple. I'm sorry, a banana, strawberry, apple, banana, right? So it's just randomly picking one of those. And so that would be the same thing that I would do when I get to the city. And if you want to infinitely randomly pick something, one way to do that is in Python, you can add a yield. And what a yield does is that a yield will basically give you one choice at a time. And so if I went through here and I said from random import choices, make a function that says return food forever, notice I can put 6 here, even though there's only 3 things in. And what will happen is it'll give me 6 random choices that constantly change, right? And so these are a good piece of code to build up these simulations, right? As if both using randomness and then also using infinite sequences in Python, you can really quickly, with just a few lines of code, build an infinite solution. So if we go back here, that's really what this choice does here. And then the NumPy, what this does is this imports that other line of code here that had all the cities, right? So I go through here and I make this into a data set. So this piece of code here takes a multi-dimensional array in this format and finds the unique cities. So it finds all the cities. And then I do a random start. So again, I just randomly pick a start here. I get the shortest route. So I sort everything by the distance, and then I return the shortest distance. And then I select a greedy path. So basically I say, every time I have a choice about which city I'm going to visit, I always go to the first choice. And then I keep track of the cities that I visited here. So I go through here, and I say for path in the city, if this is the city path, here's the city end, append, and then eventually go through and I show how many different cities that I visited, and then I go through and I calculate the total distance, because this is what I'm trying to minimize, is I'm trying to minimize how far that I go. And then what this does is it figures out the lowest of the simulation. So I'm going to do this multiple times, and then this piece of code will run everything together. So we can actually run this very easily, and if you want to run it, you could always just fork this repository. Like you could do this. What I'm going to do is I'm going to go to something called Code Spaces right here. I'm going to click on Code Spaces, and what Code Spaces does is it allows me to build out a solution without even needing to set up a development environment. I can just type in the name of this repo like this, and then I can build in this project and then start to play around with this project. Okay, so here's the project. We've got it in CodeSpace here, and notice that inside I have my greedy random start code, and this is where all the magic happens, and it's going to import some routes that are listed in a file here, and I'll show you that in a second. But basically the routes could be anything. It could be Shanghai, China, it could be London, the cities around there, it could be the East Coast of the United States, it could be the Bay Area. It doesn't matter where those different routes are going to be. The key idea here is that they're in a file here and they're all listed, right? So there's only a couple hundred. There's, again, not a ton of these, and this is just giving me the ability to make a list for this simulation. And in fact, if you wanted to grab your own routes from a different file, maybe from Google Maps or some other thing, you could easily plug them into this format and use the same simulation yourself here. So again, very, very small amount of code here that we're going to use to do our prediction. So what I would look at next is to kind of walk through our code example here, which would be in this greedy random TSP file. And in order to do that, we need to do a little bit of setup. And so some of the setup that would be involved would include making sure that we have a virtual environment. And that's really a critical step. So in order to do that, let's go through here and look at our project, look at this greedy random TSP file here. Notice that I need to change it a little bit because the name is slightly incorrect. So I'll go ahead and change this file to be greedy random TSP. And notice that at the top here, I also have the shebang line set up so that I can run it as a script. And if you do a chmod plus X, then all you have to do is // to run this. And in this particular example, we could go through here and look at the code. The first thing is it grabs that array that I set up in the routes file and just gives me all the unique cities. Next, every time I'm presented with a route, it'll sort the list by distance and give me the shortest one. And then this is the main heuristic here, which is we go through here and I travel through, I run those shortest paths, I keep track of the cities, and then at the final run, I get the total distance. And then when I run this in multiple modes, so I run multiple simulations, it'll give me the total lowest simulation. So we're ready to basically get this thing working here. And so the first thing that we would do would be to make sure that we've got a virtual environment sourced, because there are some third-party libraries like NumPy. So in my case, I've already got one created. I'll go ahead and source it. Next, what I'll do is look at this makefile here. It's always a good idea to make a project by linting it, by formatting it, by installing the software. I typically put a makefile in, especially for scientific code type projects. It can really be annoying to check out somebody's project and it turns out that it's all wrong, nothing works, and then you're left with some real big problems trying to debug the code. Maybe the code was written 10 years ago. So this code was actually written a long time ago, and I had some problems until I linted it and formatted it, and it fixed everything. And so there's a lot to like about using formatting software to fix bugs like this, and to use linting to fix bugs like this. So let's go through here and run a simulation. So the first thing that we'll do is we'll do the // right, and figure out a first simulation. Notice that we start at this first city, WFC, and then it goes to URS. It's a 0 distance. URS goes to GPS. That's a distance of 1 mile. GPS to PCG, 1 mile, PCG to MCK, right, and so on and so on. And the total distance is 129. Now it's randomly choosing this distance. It's pretty good, actually. If we run it again, you can see it's actually a much worse distance. So if we randomly start at Apple and we go to Intel, that's 8 miles, and the distance is much longer, right? It's 150 miles. And so every time we run a simulation, here's one that's actually the best one so far, and it's GPS to PCG, PCG, etc. And this is actually going to give us the best out of the 3. So this is kind of the manual way to do this. So if you had a little bit of time and you're just kind of toggling through, you're like, okay, let's try this, let's try this. But we can do even better by running lots of simulations. In this case, we'll pick 10, and it'll then give us, of all the 10 simulations, what's the route that we should go, and what's the minimum shortest distance. And in this particular example here, we see that 128 is actually the best, and in fact, it's the one we just ran before. Because it's random, we're randomly starting at cities, you never know what's going to come up. But in this case, because there's not that many different unique cities here, we're able to figure out that this optimal route is going to be 128 miles total. So in a nutshell, these traveling salesman problems are a great way to really get your head wrapped around how greedy algorithms work. And also in the real world, they come up quite a bit. If you wanted to figure out your optimal vacation, this would be a great way to do it. And again, you can go to this Noah Gift operations research repo and grab this code. If you were going to build, let's say, a vending machine, right, that someone had, like it served out beverages, maybe it's in a hotel or something like that. Like when I was in Shanghai, I remember there's a lot of really fancy vending machines that you put some money into and you get something out. But if you put in, let's say, $1, but the price inside of this is, let's say, 53 cents, how do you figure out what the proper change is? So one way that you can do this is by using a greedy algorithm. And with the greedy algorithm, the thing to be aware of is that you can essentially pick the largest coins first. So for US currency, the coins would be 25 cents, it would be 10 cents, and then it would be 5 cents, and then it would be 1 penny. You don't want to start with, for example, this, and then always give out 47 pennies, because you would run out of pennies, right? It would be very difficult for your change machine to work. So you need to have a greedy algorithm that always picks the biggest denomination first and tries to go through and give you change. So the first thing it would do would be, okay, well, we know that the change is going to be 47 cents. So maybe first we give a quarter. So then that would be 47 minus 25. And then you have 22 cents. Okay, well, what's the next biggest? We can't do another quarter. So it gets 1/4 here, and then the next thing would be you could do 2 dimes, right? So those would be the next 2 denominations. So that would be 20 cents. So you have 2 dimes, and then you'd have 2 cents left. Well, a nickel doesn't work, so then you would just have 2 pennies. So it would be 1/4. You would have 2 dimes, and you would have two pennies, right? And so this is something that's pretty straightforward to code up in Python. And so what we can do is look at this actual solution here, and this is something that we'll build in AWS Lambda. But let me just show you in code right here, which is if we see this change amount right here, and if we say, here we go, here's the change, and I want to go through here, and again, let's take the last example is my change is going to be 43 cents, right? What would that be? Well, I would go through here, and I would see 11111, and we would have 1/4, 1 dime, 1 nickel, and 3 pennies. If it was 47 cents, it would be what we talked about before, which would be 1/4, 2 dimes, and 2 pennies. So what's great about this is that it's a good solution for this problem of building change, and it works very similar to like the traveling salesman simulation or some other simulation. This is a similar kind of a thing, which is, again, you can put in any kind of a solution and go through here and figure out the correct change here, right? And this, it's kind of a similar concept, is that except for this, you're not doing multiple iterations. You're only doing one iteration to find the optimal solution. And what you can do in this particular situation is build this into a web service or a Lambda function. And so let's go ahead and let's actually take this code here and let's try this out, and I'll show you how this could work into a web service. So if we go to AWS here and we go to Cloud9, I'm sorry, to Lambda. So I go to Lambda. This is where you would build out your solution for maybe your department. You'd say, hey, look, I have an optimization solution here that gives us the correct answer. So let's go ahead and build change business intelligence. Go through here, and we'll go to Python 3.8. Go ahead and say create function. And in particular, what we can do is paste that into a development environment like this. So this is a Lambda function that will allow us to put in a payload like this. So I say import JSON, import decimal, and the event would be what gets processed by a web service, and it says if the body in the event is found here, go through and pull up the correct change here, and then return back a JSON payload. So let's go ahead and deploy this, and let's go ahead and do a test, and then we can put in let's say a change. So we'll call this change, and then I can say amount is equal to $1.34. Let's see if this works. Format it, and you can see that the answer here should show up under tests, and let's go for the results, which is, let's do it one more time. Let's invoke it. There we go. And you can see that the result shows back 5 quarters, 1 nickel. And then if I want to add a new test, as well. I could add maybe like another one, a new event. We could call this maybe the actual dollar amount, so $2.57. We could say 257, 257, $2.57. So you can build out these solutions here that give you the correct results, test them out, and now you have a web service in the making. And then to build it into a web service, you could go to add a trigger here in Lambda and go to something called API Gateway. And what API Gateway does is allows you to create an API, and then you can choose what kind of security, maybe nothing, and then go ahead and say add. And then now it actually could be built into a service where you just pass it in a JSON payload here, and you can actually do that by using something like Postman, for example, which is a tool that allows you to make web requests, or you could use a curl command that will allow somebody to test it. But the general idea here is that you can quickly, by building solutions, by building solutions in code, then convert them into business intelligence tools, and it doesn't take that much programming knowledge to kind of build these things up. So let's recap here. What are the things that we covered? So in a nutshell, we got into this idea that you can think about optimization, because it happens in business a lot, in terms of the linear solutions, which are solutions that are potentially have a nice clean answer, right? And then you have the nonlinear ones that are more complex. And the nonlinear solutions here is a little bit more complex in that you're trying to kind of figure out the optimal solution at the bottom. And so a lot of times you can use an approach where you want to get a good enough answer, and that's really the trick. Because in the real world, a lot of times you want to find a good enough answer, not necessarily the perfect answer. And so the things that you do is you do a simulation, and then also you once you've got to the good enough solution, you stop and you say, okay, this is what we're going to choose. Let's go ahead and pick this solution here. And what's nice about these call this the greedy approach here, is that you see this a lot in the real world as well, which is that you're able to, in the real world, see this with, like, let's say going across the city. When I lived in San Francisco, I would do this a lot, where let's say I was in the Embarcadero of San Francisco, which we'll call this EB, Embarcadero, and then I needed to go to, let's say, the Coit Tower, right, which is this really tall tower inside of San Francisco, and the way to get there was basically here to there. So the theoretical distance might be only maybe 2 miles, but unfortunately, the way the city streets are set up is that they go like this, right? So the city streets are basically, weaving back and forth, and then even further, each time you go to an intersection, you have no idea whether the light will be green or if the light will be red. So you have a binary choice here. The light could be either red or it could be green. So, what do you do if you have to go like this to get to the Coit Tower? What should you do? Should you, when you get to a red light, should you just wait and then go and then wait to go across the street here, and then at the very end turn? Or every time you get to a red light, should you do a greedy approach, which is just start to go in the right direction, right? And then let's say this is a green light here, then just keep going. And then maybe you keep going, and then, you have another red light. Well, at that point, maybe what you should do is that you should actually decide to either, if you have no choice, then you have to wait. But if you do have a choice, then you take like maybe a different road here, and then you go around. So the idea here is, if you are going across a city, you can use the same approach, these greedy algorithms, to get somewhere much quicker, which is that always make forward progress towards this location, rather than being very narrowly focused on trying to find the perfect solution. When you're trying to find the perfect solution, that's why it takes a long time to get somewhere. So the nice thing about optimization in the real world is that it applies to lots of different things. Or the same thing with if you're buying a house, if a house comes up and it looks pretty good. So let's actually do that. That's another similar approach to the same problem, which is, let's say that you're trying to find a house to live, and maybe the real estate agent gave you maybe they gave you the median values for your neighborhood. Let's say you're looking to maybe buy a house at the beach, and you're looking for what should you be looking for? And so maybe they said that it's $100,000 is the median home price, and then also that maybe most houses are maybe 1% or $1,000 over asking price, right? 1,000 over asking price, and then also you know that most houses are on the market for 30 days or something like this. And so then what should you do? So if you're trying to find and maybe even the square footage is, I don't know, 2,000 square feet. So we'll say footage. So what should you do? How should you approach buying a house like this? Should you be going for the perfect solution, right? Which is, maybe the perfect solution is that what you want to do is you want to get the lowest price. You want to beat the median, so you want to get like 90,000, even though the house is worth 100,000. You want to get, if they put the house up for 95,000, you want to get it for 90,000. You don't care about this, but you want maybe square footage. You want 2,100, right? So this would be trying to optimize the perfect solution, but a lot of times that's just not the way the world works. Is that it's much more like a greedy algorithm, which is that a house appears, and then you have to decide, basically, is it good enough, right? So for me, the way I would I would use a greedy algorithm, which is, if it's close to the median values here, is you offer the median price, right? So you say, if a house is 2,000 square feet and it's 100,000, then maybe I offer 100,000, and then you give them maybe 24 hours to respond, and then maybe they come back and they say, nope, you need to do 110,000. You just say, okay, thanks, next. And then you go to the next house and you say, okay, again, 100,000. And then they say, okay, how about 101,000? And you say, well, because I'm not trying to find the perfect solution, let's go with this, right? And we'll stop. And then that's my optimal solution. So if you look through the world, you'll see this greedy algorithm approach. It happens all the time. And what it means is that you don't need to find the perfect solution. You just need to find one that's pretty good, and that way you can save time, you can save money, you can save distance, and it's a good approach for someone with a business background to think about. So let's keep going with business intelligence solutions here. The other topic that I wanted to get into is kind of similarly, is this with machine learning, business intelligence, with optimization problems. Also, do you write the code yourself, or do you use other solutions that are much quicker potentially? And so one way to think about this problem is through using no code, low code, off the shelf tools. And Amazon in particular has a lot of these no code, low code tools. And let's actually just shift gears and talk about those. So on Amazon, what are some of the low code, no code solutions that you can use to quickly come up with solutions? So it's kind of the same thing. It's a greedy algorithm. On one hand, you can write all the code yourself, which is fine. And you see the problems, though, is that, like in my example here, that I had my code was broken, right? And now I have to spend time fixing it. Why do I want to do this? And then on the other hand, you have no code. And there isn't a perfect solution, but there's some variant. No code means there's no fixes, right? There's nothing to fix. So maybe the middle ground here is you have a little bit of both. And in particular with business intelligence, that in business analytics, that there's some great tools that don't require a lot of effort on AWS. And the tools on AWS that we're going to talk about briefly are called Data Brew, which is a exploratory data analysis tool that is a very new tool. And there's also a tool called Quicksite. And so we'll take a look at both of these tools here. And if we have time, maybe we'll also look at an AutoML solution that's pretty neat as well. But basically with, I think it's spelled Quicksite like this, and Data Brew. So Data Brew can do EDA, so it can automatically figure out the statistics for you. Quicksite can do basically Tableau or automatic graphing for you, and can easily help you find patterns without writing any code. And then AutoML can automatically do things like classify data. And these are really just point and click solutions here. So let's go ahead and take a look at these point and click solutions here. So if I go to the management console and I go to, let's say, Data Brew, let's take a look at this first. The way this tool works is that you can create a project from scratch here, and we can just say maybe business analytics like this. And then it's going to ask me to, what do I want to do? We'll create a new recipe, and then it will select either an existing data set, a sample data set, or a new data set. So you could actually pull in your own data set here and upload it from a bucket, or you could even do a file upload. In our case, I'm going to go to a GitHub repo and just grab a data set real quick. I have one called in social media, social power NBA here. I have a pretty good one. Let's go to data, and let's go to this one. This is like some salary data from the NBA, and I'm going to just download it. So click on raw, and then I'll say file, save as, and then I'll just download it to my desktop. And then I'll go here and I'll select file upload, and then we'll just upload this data. And what's irritating is I need to rename it real quick. So let me just rename this real quick. So here we go. Let's go to I'm gonna just Safari, I think, name this, put an extension on it to make things more difficult for me. And let's go to desktop. There we go. I'm gonna just take off that ending for it. Yeah, pretty irritating when browsers modify the data. Okay, so there we go. We'll choose this file. Now it's been changed. Okay, and then it'll ask us the format CSV. Treat the first row as a header. Perfect. This looks good. Let's go ahead and create this project. Oh, we got to call it NBA. We'll just call it NBA, and then select a destination. I'll just pick some location here. Sure, that works. And let's go ahead and choose a role. I'm going to choose a role that has the privileges to do stuff to it. There we go. So it's going through and it's going to grab all this data, manipulate it, and basically perform an exploratory data analysis on this data. So let's give it a second. There we go. So it's provisioning compute. So behind the scenes, it's doing stuff like a data scientist would do, formatting it, cleaning it. Now notice as well some of the things that Data Brew can do, including formatting the data, cleaning the data, extracting the data, finding missing values, duplicates, all kinds of really fun stuff. And that's what's great about these high-level tools. And there are more and more of these tools being developed by multiple cloud providers, by multiple platforms that really take away some of the annoying things about writing code. So I'm going to let this run for a second, and I'm going to go back to another data set that I already had here. And we'll come back to the NBA one. And notice that this is a baby name data set. And if we look through here, we can actually look at all of the descriptive statistics, like how many values there are, how many columns. We can also look at the statistics of the columns. So we can see here's the count, the gender, the ID, the name, and basically it shows us that top distinctive values here. And in particular, you can toggle between. If I click on gender, for example, it shows you, obviously in this case, there's either male or female. There's actually much more female length. There's 9,607 male names, but there's 10,000 female names, which is pretty interesting. Maybe there's more variation with female gender names. And if I click on name here as well, you can see that there's a total of I think distinct 3,431 names. And then here's the top distinct values. You can see that some of these are selected, basically 18 times. Like John was all these, and it shows, missing values, cardinality, and even data lineage. So the data lineage says, well, where did I get this data from? Well, first I got it from S3 bucket. I put it into a data set, and I then build out a project, and then I took the results and I put the results here. So this would be what you would do as a data scientist or business intelligence person, maybe to start with, is you just first clean up the data without writing any code, and you get to find all these really good descriptive statistics about it. Let's look at my other project and see if it's already done. This is the NBA data set. Let's see if this was done here. It looks like it's still working potentially, maybe on this data set. So if it is, I'll come back to it. No, here we go. It's done. So you can see here that if I wanted to do more data, I would run a data profile, and it would profile the data. And let's go ahead and do that. And we'll say, there we go. And we'll profile the data. And then if I also wanted to go through here and do other things to the data, like, for example, I think the other thing that it could do was give me the column statistics. Okay, so it's finding these out real quick, and it should be just a second to find these out. Let me show you one other thing. While this is all running, I want to show you the Quicksite. So a different approach that you can use is this tool called Quicksite. And with Quicksite, it allows you to do something kind of similar, except for this is even more streamlined in that you just need to feed it a data set. So you can say new analysis like this, and you say new data set, and you just upload data from a CSV file or point it to some other location in Amazon, right? Like S3, for example. But let's go ahead and upload a file. We'll pick that same data set. It goes through, it previews it, and it goes through and it finds that, maybe there's some, well, it looks like I must have downloaded some bad data. That's so which is helpful because it shows me that I messed up downloading this. So what I should do instead is I should say file. I should maybe say, well, I don't know why Safari is messing all this up here, but basically I've already got this data loaded into data prep here. But that is actually helpful, that you can immediately see that there was a problem with it. And so instead, I can look at potentially a previous upload. Here we go. And you can see that if I create an analysis, that I've got all these different variables here that I could choose from. So I could look at maybe the salary in millions, and maybe their player name, and maybe their favorite counts, and I can just start building up these these visualizations with again, by just exploring the data. So I can kind of compare here. Okay, well, let me look at how much money they make compared to the how popular they are on social media, right? And if I pick at as well, maybe the wins, like can we find out, how many wins they have? Here we go. Here's their wins. There we go. So we could even maybe take off the salary for a second, and we could look at the retweet count here, which is this one, and then how many wins they have total. And you can see that, in fact, potentially the really popular players, they may have some kind of a relationship with wins, right? So we can see that on social media, some of the most popular players have the biggest accounts, right? So we can see here's LeBron James, and there's another visualization that I had earlier that I can show, which is this one, that shows us that, in fact, in this particular example, that with page views, this would be Wikipedia page views, that the more wins you have, you can see that the more popular, or the more page views that are actually generated, right? This is the sum of the wins, the page views, and the blocks. So you can see that there's actually like a super linear trend here for page views and wins. So without writing any code, and before I do any machine learning at all, I can look at this and say, this looks interesting. I can actually maybe build a machine learning model in the future, either through AutoML or through some other technique that could predict the amount of wins, potentially by using something like page views, right? Because look, we see there's a trend here, right? And it looks like it's not even linear, right? A linear trend would be here. It looks like the trend is actually super linear. And if I wanted to as well, I can pick on these other tools here, and they'll maybe show me other values. So what would be the next step here? Well, I think one of the things that could be done is that we could potentially grab this data and bring it into another tool on AWS. So one of the tools that you can explore on AWS is called machine learning. So if we go to console here, and it's an AutoML. So we've already done Databrew, which does auto EDA. We've done Quicksite, which does quick exploratory data analysis, and then the other one would be machine learning. And machine learning is a service that is been kind of migrated to AWS SageMaker, which is their machine learning platform. But the concept is the same, which is that you create a new data set here. You say data set in ML model, you upload it, you give it a location, you give it a name, and once you do that, then it goes through and allows you to kind of run this wizard. In fact, if I look at a data set here, let's look at a data set, and I'll run this again. So here we go. Here's a data set, which is right here. And if I go and I want to build this from scratch, let's go ahead and do this. Let's say Amazon machine learning. create new data source and model, paste this in. What's nice about this kind of an AutoML tool, we'll just call this bank data, is that it will figure out the schema for me automatically, ask me whether the first one is a column head. It finds all this data for me, categorical, numerical, and then we'll say, you're trying to do a prediction. Well, what do you want to predict? I'll select that I'm going to try to predict this, which is whether someone responds to a marketing offer that's in my bank. I'll go through continue, and then what it will do is it'll ask me for basically what am I trying to do, and it says you're trying to do a ML model, and I'm going to give you some good recommendations here, and I'm going to split the data into training data, and then go ahead and run this model for me. And it even goes through and it does things like shuffles the data, adds regularization. So all the things that we saw in the TensorFlow tutorial. And then if I go through here and I run this, it'll go through and it'll do a prediction. So if we go back here and I go back to machine learning and I look at a previous one that had been run, so let's go to this one, what it will come up with is that it'll show me an area under the curve prediction. So it shows me exactly what I wanted without writing any code. And I can even go through here and kind of go back and forth and skim through everything. So the idea here is that there are lots of ways to do predictions and to come up with solutions. And a lot of times you don't need to have a perfect solution. You can instead come up with one that's good enough. And then even in the case of machine learning, you can, I guess at a meta level, the same thing applies where you may not want to write a bunch of machine learning code if you can come up with tools that solve your problem without writing code. Because as we saw from the other example where, maybe you're in a hurry and you sure you could debug the code, but why spend all this time going into debugging the code when you're just trying to come up with a quick solution. So that's really the gist of what I wanted to cover today, is that there's high-level tools that can solve a lot of problems, and also approaches as well that can solve a lot of problems. And the cloud in particular, I think, has a lot to offer in terms of building these very quick solutions that help you debug things. And then again, how much code do you want to write versus a lot of times you can come up with great solutions with very little amount of code. And in particular, things like Quicksite, I think was the one that I think is really got a lot of promise, is that you can just click a button, come up with some kind of a solution, paste that into a report for an executive in a company, and you may not need to get deep into code and explore it. Maybe you do, but first try the greedy algorithm, right? Go for the shortest approach, and that might be good enough. And by the way, the other thing I'll share about this is when you do come up with something that's useful, like this solution here, you can also share it out, publish it to other people.